Chapter 5 deals with applications of Newton's laws. There's a lot of really good problem solving that goes on in Chapter 5. And so I really want to break Chapter 5 apart into kind of smaller chunks. So this video is just going to look at equilibrium, or Section 5.1. When something's in equilibrium, it simply means that if you add up all the forces, it would equal 0. Or another way of saying that is that the net force will equal 0. Now, for a linear problem in one dimension, this is really easy. It means that if there's a force of 20 newtons to the right, there must be a force of 20 newtons to the left. Pretty straightforward. This is true whether or not that object is at rest. That's called static equilibrium, when something's at rest. Or whether this object is moving at a constant speed in a straight line. If it's moving and it's in equilibrium, we call that dynamic equilibrium. But when something's in equilibrium, we know that all the forces add up to equal 0. So let's look at our first example of an equilibrium problem. And it deals with, this is in the book, a car engine. And the car engine is suspended. I'm not going to write all the words because it's in your book and it's in my notes. But they give us a picture. Here's our picture. There's a ring. And there's 3 chains. There's a chain that goes this way. A chain that goes this way makes a 60-degree angle right there. And a chain that hangs straight down supporting this weight W. They tell us the car engine weighs W. They labeled these chains T1, T2, and T3. And they tell us that it's a static situation. The car engine is just hanging there, it's not moving. And they want to know the tension in each one of these chains. So we start off going, well, I know that the net force is 0. That tells me something really important. It tells me that the net force, or the sum of all the forces that are horizontal, will equal 0. And the sum of all the forces that are vertical is going to equal 0 also. All right. We really kind of want to break this up into 2 parts. I'm going to draw 2 free body diagrams. The first free body diagram I'm going to draw is for the engine. If I look at the engine, which is this block right here, it has 2 forces acting on it. The weight is pulling down, and the tension in the first chain is pulling up. Well, since this is a static situation, this is that simple one-dimensional problem, the first thing I know is that T1 has to equal W. That's actually part of our answer because the directions are asking us to find the tension in each chain in terms of W. It might actually feel like an easier problem if they said find the tension in each chain if the car engine weighs 2,000 newtons. Well, if the car engine weighs 2,000 newtons, then T1 has to be 2,000 newtons. Because when I draw this free body diagram for this engine right here, there's only 2 forces acting on it. Gravity is pulling the engine down, and the tension in chain 1 is pulling up, so that the net force is 0. So that's really pretty easy. To find out the tension in the other, we want to take this ring right here that the chains are connected to and do its free body diagram. So here's our ring. We see that T1 would be pulling down on the ring, and we happen to already know that that equals W. We see T2 is pulling in the negative x direction, And then we have T3. Now I want to be careful with T3. Here's our x-axis. I normally measure angles from the positive x-axis. But I have this one measured right here, but if I think about it, if I draw this axis, I can see that this has to be 60 degrees. These two angles, if you remember your geometry, they're alternate interior angles of a transversal. Or you could just say, hey, let's make this a right triangle and let's think for a minute. This angle would be 30, so this has to be 60. Either way you do it, we know that that angle is 60 degrees. Since they asked me to get T1, T2, and T3 all in terms of W, let's go ahead and put a W here. I know what T1 is. T1 has a force, a magnitude of W. All right. Anytime you have forces that don't lie in the X or Y axis, you want to get those components. That's the first thing you want to do. That's going to be really easy. I can replace T3 by its components. T3x is T3 cosine 60 degrees. Well, if you remember your special angles from geometry, and you may or may not, or from trigonometry really, if you do cosine 60, it comes out to be exactly 1/2. So T3x is simply T3 over 2, or 1/2 T3, however you want to say it. I'm going to put T3 over 2. All right, now we need the y component. T3y is T3 sine 60. And that one you may not remember, but the sine of 60, you can do it in a calculator and get a decimal. It's like 0.866, whatever. Or for right now, I can just say, hey, sine 60 is √3 over 2 T3. That's T3y. That's how much of it is going up. Well, the whole point in getting the components is that you can now kind of make a new free body diagram if you like. The original free body diagram is correct. You should always draw free body diagrams showing the forces acting, not necessarily the components. But once you've got that, you may want to draw another one. So now we have this. We have W pointing down. We have T2 pointing to the right. We have T3x, which is T3 over 2. And we have T3y, which is √3 over 2 times T3. So we took this vector component, this vector T3 at an angle of 60, and we wrote its components. Horizontally, cosine 60 is 1/2, so that's T3 over 2. Vertically, sine of 60 is √3 over 2. Like I said, we'll get to decimals in the end because we don't usually keep things exact when we're dealing with measurements, but for now that helps. All right, I want to erase so I have some working space, but you can see how we got the components. Free body diagrams tell me everything. Remember, my goal is to get everything in terms of W. So I think I start vertical right here. I'm going to change colors one more time. W has to equal √3 over 2 T3. which means T3 has to equal 2 over root 3 times W. Now I think I'll bring in the decimals. What is 2 divided by root 3? Came out to be 1.1. Five, 4, 7. Now, that's way, I don't really know how many significant digits we want. If we want to be exact for right now, we can leave it like this. If we want it as a decimal, that's what T3 is in terms of W. So really, we do have an answer. We have an answer that says that in terms of W, and I wrote 3 significant digits. I'm just going to say that's how many we want. All right. That was the horizontal equation. Vertically, that was the vertical equation, up and down. If we look across or horizontally, we get another equation that says that T2 must equal T3 divided by 2. Well, that is 1.1547 W divided by 2. $1.1547 divided by 2. Get something like this, but again, that's way too many significant digits. So T2 I have a typo. Sorry, I typed something in wrong. Let me fix that. 1.1547 divided by 2 is 0.5735. There we go. So again, when we write down this answer, to 3 significant digits, we don't actually know, the tension unless we know the weight. But if I do know the weight, it's really easy now because I've got all of those in terms of W. So for example, if W is, I think I have one in my notes, 2,210 newtons, then T1 is 2,210 newtons. T2 was 1.155. I kept an extra times 22 to 10. It comes out to be 2550. Again, I'm just keeping, that's T3. I did T3. I'm just keeping 3 significant digits. And T2 only comes out to be 128. Nope. Having trouble typing it in. There we go. 1,280. newtons. I'm not surprised when I look at the picture that there's less tension here. Obviously, I expect most of the tension to be vertical because the weight is pulling down. But it does need to pull back just a little to balance that force from T3. Okay, there's our first example of an equilibrium problem. The approach, draw a free body diagram. Any vector that doesn't lie on the x or y axis, we want to take that vector and get its components so that it does lie on the x or y axis. Okay, let's do another example. Let's look at a car on a frictionless ramp. Only the cable prevents the car from rolling, or sliding for that matter. Okay, so what's this look like? We have a ramp or an inclined plane. There's the ground. And it makes some angle of alpha with horizontal. Up here we've got a car. It's got big wheels. And normally if it was on a frictionless surface, it would just slide down. But we've got a rope connected here. I don't know what it's connected to, but the tension in that rope keeps the car from moving. Okay? So we have a cable that stops it from sliding downhill. Now, we need a free body diagram. And the free body diagram is going to lead us to some interesting ideas, some really important ideas on how you're going to solve problems when you're dealing with an inclined plane. I see three forces that are acting on this car. One, of course, is this tension in this cable. There's a cable pulling it up at some angle. There's tension. One is the actual weight of the car itself, which points straight down. And the third one is the normal force. Now you'll remember the word normal means perpendicular. The normal force is always exerted perpendicular to the surface. So in this case, remember this rope is parallel to the surface. That's very important, that the cable's parallel to the surface. And the normal force will be perpendicular to the surface. These make a right angle. We have to get everything in 2 dimensions. The easiest way to do it is going to be to let the direction of the ramp be the direction of the x-axis. That's going to be helpful in future problems too, because if we have a car and it's rolling up or down the ramp, it's going to be moving along the x-axis. You'll notice that means the tension points in the positive x-axis direction, and it means the normal force is in the positive y-axis direction. 2 of our vectors are already lying on this axis, so it makes it the correct coordinate system to use, the one that's going to make things easiest. If I continue this, then that would be the negative x direction. And this direction would be the negative y direction. We got to figure something out. We got to figure out how to take and break this into components. If we go back up to our original picture for a minute and we think about it, the weight points straight down. You can see that it makes this triangle right here. That angle is going to be 90 minus alpha. If this angle right here, that's this angle right there, is 90 minus alpha, this angle right here is alpha. We could have used theta, the book used alpha, so I'm using alpha, but that's our angle. All right, I think it will help if I draw a picture. We have a weight hanging straight down. We have our y-axis points this way, and our x-axis points this way. There's my right angle. This has two components. There's W. This side of that right triangle is WY, because that's on the y-axis. And it also has a component that points this way. That's WX. If I drew them on the actual picture, it would look something like this. This vector goes in the x direction that far, and it goes in the y direction this far. But it makes that right angle. This is alpha. Let's go back to our trig identities. Let's start with sine. We know that sine alpha equals opposite over hypotenuse. In this case, opposite is WX. The hypotenuse, of course, is W. If I solve for WX, I get that the WX is W sine alpha. In some books, rather than call it the x component, they may call it the parallel component because x is parallel to the ramp. So you sometimes might see that as W parallel. W parallel or WX are the same. But notice it equals sine alpha. That's different. In every other application in this book, we're measuring angles from the positive x-axis. Well, if we measure angles from the positive x-axis, then the x component is cosine theta. But this is not being measured from the positive x-axis. In fact, it's being measured from the y-axis. And it's because we're measuring from the y-axis that we get a different result. So, the horizontal component or the parallel component is given by W sine alpha. If I do the same thing and I use my cosine alpha, of course, is adjacent over hypotenuse. So I end up getting that cosine alpha. Adjacent is WY. Hypotenuse is W. And I end up getting that WY is W cosine alpha. This is sometimes called the perpendicular component because y is perpendicular to the ramp. So we could get that W perpendicular. That little symbol means perpendicular, just like the two parallel lines mean parallel. Or WY is W cosine alpha. Now the good news is we don't have to figure that out every time we solve a problem with an inclined plane. We only have to figure it out once. When I'm on an inclined plane, this is how I get the components of the weight. The component of the weight parallel to the ramp, or you could even think of it as being down the ramp because part of the weight is trying to pull it down the ramp, is going to be W sine alpha. The part of the weight that's perpendicular to the ramp is what presses against the ramp. This presses against the ramp. So that's going to be really important for any problem we do on an inclined plane. So we've taken a whole big part of this problem just to figure out what do I do with the weight. But now I've got it. So I'm going to do a little erasing. I'm going to write down what's important. And the important thing that I know is Wx is W sine alpha, and Wy is W cosine alpha. Those are the size. If I want to redraw this free body diagram, now I can, or I can take the old free body diagram and I could erase the weight. Let's just redraw it. I have tension going up the ramp, and I have Wx going down the ramp. I have a normal force perpendicular to the ramp, and I have Wy also perpendicular to the ramp. I can answer some questions in terms of the weight and the angle. The tension in the cable is going to equal Wx. So the tension in the cable is W sine alpha. The normal force is going to equal Wy. So the normal force has to equal W cosine alpha. Again, we don't even have any numbers. We're just looking at things. Now, this is actually what they ask us to find. If they tell us the weight and they tell us an angle, I can very specifically tell you how much tension is in that weight, and I can tell you how much the normal force is. So let's look at an example. Let's fill in some numbers. If the car has a mass of 1,200 kilograms and the angle is 26 degrees. Here's where we have to be so careful. We've worked so hard that students often make a mistake right here. We need W. We don't want to put 1,200 kilograms in for the weight. The weight is mg. So the weight is 1,200 kilograms times 9.80 meters per second squared. If I do 1,200 times 9.80, let's see what I get. I'm going to get something, my notes, I have the car is 1,200 and then I have it as 1,250. So when you read my notes, there's a goof. 1,200 times 9.80 is 11,760 newtons. I don't want to round it because it's not my answer. So the tension in the cable is W sine alpha, 11,760 newtons, sine of 26 degrees. So I just take that answer and multiply by sine of 26. And I get 51, 55, and some change. I only have two significant digits, so I'm going to say that the tension in the chain is 5,200 newtons for that specific example. And the normal force, it's W cosine alpha, is 11,760 cosine 26 degrees. So 11,760 cosine of 26. And I get that the normal force to two significant digits is 11,000. You'll notice the normal force is very close to the weight, that it's no longer the full component. In fact, the flatter this ramp is, when it's completely flat, the normal force will equal the weight. The steeper that ramp is, the less the car is pressing against the ramp and the more the car is trying to roll down the ramp. Okay, so there's our second. It too was an example of static equilibrium. Nothing's moving in this example, but we had a really important lesson, and that was how do I take the weight and break it into a horizontal component or a component parallel to the ramp, and how do I break it into a vertical component or a component that's perpendicular to the ramp. Okay, let's do one more. This is a case where it's not static, that it works exactly as if it was because it is still equilibrium. It's moving at a constant speed in a straight line. In this example, we have a cart on a ramp. They tell us that the ramp is 15 degrees. Here's our cart. It has a weight they're going to call W1. They could have given me a mass and called the mass M1, and then the weight would have been M1G. But they told us the weight we're going to call W1. Okay. It is connected, being pulled along, and it's connected to this pulley. And over the pulley, we have a bucket. I think this involved coal or something, but I don't have the backstory anymore. But we have a bucket. We're going to call this T2 and this T1. And the bucket has a mass of W2. So we have a cart and we have a bucket. The cart and bucket are moving at a constant speed. They're also both moving in straight lines. They're not moving in the same straight line, but they're both moving in a straight line. Okay. The other thing that we want to know that they tell us in the problem is that this is an ideal pulley. In an ideal pulley, there is no mass, there's no friction. So if you have an ideal pulley, the tension in that rope is the same everywhere. And I might add it's a massless rope. This is a massless pulley. It's a frictionless pulley. And in those situations, the tension in the rope right here, T2, will be exactly the same as the tension right here in T1. Okay. We don't have any acceleration, so this is an equilibrium problem. They want me to find, what do they add? The relationship between W1 and W2 for a constant speed. How is W1 related to W2 if we have a constant speed? Now, we have two different objects here. Anytime I'm solving a problem with two different objects, I'm going to need two free body diagrams. We dealt with that a tiny bit in our first example, where we had the engine block, and then later we looked at the ring. Well, in this case, we clearly have a bucket, and we clearly have a cart. The bucket one's the easy one, so let's start there. The free body diagram for the bucket looks like this. The weight of the bucket, which we've called W2, is equal to the tension. Notice since T1 and T2 are equal, let's just call them T now. There's only one tension since it's the same. So W2 has to equal the tension, or the tension has to equal W2. But that's obvious. So T equals W2. Well, that's what the first free body diagram tells us. It does not matter whether this bucket is being raised and the cart's going down the ramp, or whether this bucket's being lowered and the cart's going up the ramp. The part that matters is we know it's moving at a constant speed, and we know it's moving in a straight line, whether it's moving up or down. Let's look at the free body diagram for the cart. Now, the free body for the cart's more complicated. We know that the tension's going up. Again, we're not dealing with any kind of friction. We're not there yet. We know that the normal force is perpendicular to that. And we know the weight is straight down. Call that one W1. Now, I'm going to go ahead and take W1 and break it into components. I know it's got this component, call that WY, and WY is going to equal W1 cosine 15 degrees, because this time I do know the angle of the plane. It also has a component down the ramp. We call that WX. We know that WX is going to equal W sine 15. Again, that's W1. If I take and I replace W1 with its components, my new picture looks like this. That looks really pretty nice. And I'm trying to get a relationship between W1 and W2, and I think I see it right here. I know I know that the tension, rather, is equal to W2. So if I want a relationship between them, I know that W2 equals W1 sine 15 degrees. That is a relationship. That's really all I have to do to answer the question. Now, if I know one of the weights, I know the other weight. But that's going to be the condition for it to move at a constant speed. Okay, so that's our third example. So we're going to be done with equilibrium problems. We'll probably do some more in class though.